everyone, we are continuing with our unit on right triangles. So as a warm-up, what I'd like you to do is take a look at the following questions and see if you can come to a conclusion. If you have access to a graphing calculator, it might help if you went ahead and plugged in and looked at the graphs to see what happens as we approach 90 degrees. If you do not, you can use Desmos or just use a graph or a chart, any of which you could find online. Okay. So go ahead and pause the video, see if you can come to a conclusion for these questions. Okay, so if you take a look at our graph, so if you have a TI-84, if you have an Inspire, it's a little bit different, but if you have an 84, you can plug in your function. I've only selected the top function here, y1. If we go to zoom, I'm going to use zoom trig. And I see my sine graph does this. And right here is going to be my 90 degrees. Okay, so it looks like I approach 1. Hey, now if we take a look at cosine, so I'm going to deselect sine and go down to cosine. Slightly different graph, okay, but more or less the same. And as I approach 90 degrees, cosine approaches 0. Right, it looks like I go to 0 here. Right, now tangent is the weirdest of the bunch. So if I look at the graph of tangent, you're going to get a lot of, they look like cubic functions. Right, there's a lot of them. And what this calculator is incapable of showing is that you actually have vertical asymptotes. What's going on? Vertical asymptotes all down here. Okay, so this is actually just a continuously repeating function that will go on to infinity like this. And we're asking what happens to the value of tangent as x approaches 90 degrees, which is going to be right here. I have a vertical asymptote, so tangent actually approaches infinity. Okay. Now, as we covered last time, the value of tangent of 45 is my easiest one. Tangent of 45 is going to be 1. Okay, and when does the value of tangent become greater than 1? So let's take a look at our table and see what's going on here. Wow. So right off the bat, I notice I have a lot of very small numbers here, okay, and x is, again, very small. So what's going on is I'm looking at my degrees, so I'd have to scroll quite a bit in order to see what's going on further down in my y column. So what I'm going to do is go to table set. I'm going to ask my table to ask me for my independent variable, okay. Alternatively, if you know kind of where you want to start, you could have your table start at not 0. So let's say I started at 45. And I go back to my table. Right, now I see I am below 1 here, I'm above 1 here. If you set your independent to ask, then your x column will just be blank, and you can type in whatever number you want. Okay, so 45, I know I'm 1. 46, I know I'm greater than 1. Okay, so what we're going to talk about today is inverse. All right, so a little bit of what we talked about last time, how sine is its own operation, and we can't get rid of sine unless we know the inverse. Well, now we're going to talk about the inverse. All right, so some things to think about. What is the inverse of addition? All right, subtraction. What's the inverse of multiplication, which we know is division? So then, is there an inverse of sine? So that would probably have to be its own operation in and of itself, and that's what we're going to find out. So what we're going to say is that if we have some sine of a being x, then the inverse of sine of x is going to be your angle A. Okay, so kind of thinking about opposites here. Now what's weird about our notation is I have a sine of -1 here, and if you see like some function of to the -1 power it looks like, it does not actually mean to the -1st power unless the problem specifies that. This always means inverse. And we will learn more about inverse functions later in your math lives. But for now, if you see -1, that means inverse. Alternatively, another way of writing inverse sine is to put arc in front of it. So arc sine would be the same thing as this. Arc cosine is the same thing as this. Arc tangent is the same thing as this. It's just another way of writing it. Later, at least for now, it doesn't really matter, but later in trigonometry, this will be my preferred notation because it's less confusing, because we will end up using exponents with our trigonometry, and then it gets confusing if you want it to actually be to the power of -1, or if you're looking for an inverse. Okay, so if you use arc, you'll never have that confusion. Okay, so we can actually use our calculator to find each angle measure. Again, if you don't have access to a calculator right now, then that's fine. You can use any online calculator, or just take my word for it. But at least for the TI, if you know where your trig buttons are, then if you hit second and then your trig button, then that will give you your inverse trig. Make sure that you are in degree mode. So here, if I am finding inverse cosine of 0.87, this will actually give me 30 degrees. And that makes sense because, well, as you get more comfortable with the decimals, you'll kind of know what 0.87 represents. It does represent one of our perfect values on the 30, 60, 90 triangle. Okay, and so now I'm looking for inverse sine of 0.85. So if you try that, you will get 58 degrees. And inverse tangent of 0.71 is 35 degrees. Okay, so right now we have to think about what we're inputting and what we're receiving as an output. So for each of these, I have an output of an angle. What I'm inputting is actually a length. Hey, this is the length of a triangle. That is my input in this situation. And I'm outputting an angle. So what we mean by inverse is this is the opposite of what we were doing before, right? So if I think about what I was doing before, if I was trying to find sine of an angle, right? So I would always input an angle, and this would always give me a length along my triangle. So if this was my angle here, my length would be here divided by my hypotenuse, right? So A over C. So it's a ratio of lengths, or just a length, depending. So I am inputting an angle, I'm receiving a ratio of lengths. Now in this case, I'm doing the opposite. So now I'm inputting my ratio, or my length, and I am receiving an output of an angle as a result of this. And that's what we mean by inverse. That's what an inverse is. It doesn't always mean opposite. It's not always as clear-cut as multiplication and division. What we mean is your input and your output actually switch. That's what an inverse is. Okay, so now if you have access to a calculator, go ahead and try these. See if you get the same answer as me. So go ahead and pause the video and check to see if you got what I got. Okay, and I got 37 degrees, 87 degrees, and 42 degrees. I just rounded to the nearest degree. Alright, next example. So what I have here is a right triangle with legs of 8 and 15. Now I want to find the measure of the angle opposite the 8-inch leg. So opposite 8-inch, so that's going to be right here, that's angle A. So I want to find the angle measure here. Now, could I find the hypotenuse? Absolutely. I could use the Pythagorean theorem and find the hypotenuse, but I don't need to do that. If I have two values, I can just refer to my handy dandy SOHCAHTOA I have an opposite and an adjacent to my angle, so I'm going to use TOA here. So I know that tangent of A is 8 over 15. Alright, now I need to solve for A. I need to isolate A, which means I can't have this tangent here. So the way that we'll actually use our inverse trig is, it's similar to multiplication, but it's not actually. I'm applying a whole new operation. I'm applying inverse tangent to both sides. Okay, so they will counteract each other. They'll kind of cancel out. Again, I am not multiplying. I'm not multiplying. Okay, I always have students think that I'm multiplying. I'm not multiplying inverse tangent to tangent and they're canceling out. That's not what I'm doing. It looks a lot like that's what I'm doing, but that's not what I'm doing. I'm applying a whole different operation in and of itself. Alright, so what that leaves me with is just A being inverse tangent of 8 over 15. Okay, so if we solve, that will give us 28 degrees. Okay, now what is the length of AB? I could solve for AB now in a variety of different ways. I could use sine, I could use cosine, because I know my angle measure now, or I could use the Pythagorean theorem, totally up to you. This is just be 17. Okay, and then last part here, I want to find the measure of the angle opposite the 8-inch leg using sine. Okay, so now that I know that this value is 17, I want to use sine. So I know that sine of A is going to be opposite 8 divided by 17. Same process. Now I want to apply inverse sine. Okay, so another way of thinking about this is, if this is what I'm given, sine of A equals 8 over 17, then that means, again, inverse sine of whatever was on the other side of the equal sign is equal to your angle measure. So I can just rewrite this as my angle measure equaling inverse sine of 8 over 17, okay, which is 62 degrees. Alright, if this is all confusing, totally understandable. It's a whole new operation, right? It's just like learning multiplication again for the first time. It's totally own thing. Hey, but with a little bit of practice, I promise it'll get easier. Alright, so next example, we'll do a few more examples together, and then I will leave you to it. So I have a right triangle, PQR, with a leg of 5 inches in length and a hypotenuse of 5 root 2. So that automatically tells me that I have a 45, 45, 90 right triangle. So I want to use trigonometry to verify that I have a 45, 45, 90 right triangle. So first thing I'm going to do is draw a picture. Okay, so I have PQR with a leg of length 5 and a hypotenuse of 5 root 2. Okay, so let's just use this angle right here. You could use either, it doesn't matter. I'll call this angle X. Now I see that I have an adjacent side and a hypotenuse. So if I have cosine of X being 5 over 5 root 2, then essentially I'm asking cosine of what angle equals 5 over 5 root 2, which if I simplify that, I get 1 over root 2. So I'm asking you, cosine of what angle equals 1 over root 2, which this is a special value within trigonometry. Okay, so another way of saying this is x equals inverse cosine of 1 over root 2. Okay, which if you plug that into your calculator, you'll get 45 degrees. Alright, next example we are asked what kind of triangle is PQR if we have side lengths of 5, 12, and 13. So hopefully you recognize this is one of our perfect Pythagorean triples. And let's set up a totally to scale triangle. That's actually not bad. So for our picture, we'll say this is 5, 12, and 13. Let's label this angle X and this angle Y. Okay, so I just need to set up some ratios here. So sine of X would be 12 over 13. Okay, so if I solve for x, I would end up getting inverse sine of 12 over 13, which is going to be 67 degrees. You can just use your property of triangles to find y, or we could set up our own sine for y. So sine of y would be 5 over 13. Okay, let's clean that up a little bit. 5 over 13, so that means y would be inverse sine of 5/13, right? So 23 degrees, which makes sense, right? That falls along with what I assumed I would get. Alright, a few more examples. So I have a 15-meter pole leaning against the wall. The base of the pole is 10 meters from the wall. Find the angle that the pole makes with the ground. Okay, so here's my wall. Here's the angle I'm looking for. Okay, the 15-meter pole is represented by the hypotenuse, and the base of the pole is 10 meters from the wall. So I'll call this x, and I am looking for some relationship that has a relationship of adjacent to hypotenuse, right? So if I go back to my trusty SOHCAHTOA, then I'm looking at CA here. I'm looking at cosine being adjacent over hypotenuse. So that means that cosine of x would be 10 over 15. So that means x is going to be inverse cosine of 10 over 15, or arc cosine, you could also say. So that means x would be 48.2 degrees. Alright, next example, find x. So round the answer to the nearest whole number. Okay, so I'd like you to give this problem a shot and see if you got what I got. Go ahead and pause the video and attempt the problem, please. Okay, so I'm going to be using my adjacent over hypotenuse relationship. So that's cosine of x being 8 over 20. So that means x is going to be inverse cosine of 8 over 20, meaning that x would be 66 degrees. Okay, now they want us to solve these without a calculator. So what we're given is, if sine of a is 0.5, find the measure of angle A. Okay, so that means that A is going to be the inverse sine of 0.5. So looking back at our notes, what I'm asking is, for what angle of where I'm using sine do I get an output of 0.5? Okay. And so if I look back at my notes for my perfect trig values, that would be for 30 degrees. Right, similar problem here. So tangent of y equals 1, find the measure of angle y. So remember, this is our easy one. So what I'm asking is for inverse tangent of 1, but really I'm asking when does, for tangent of what angle equals 1? And I know that's going to be 45. And again, that's just from our previous notes. Alright, just a few more examples here. So I'm actually just going to do one of these and then leave the other two for homework. So what I am given here for example 8 is to find the value of f. So f is right here, and I know that since this whole length here is 28, then my small length here will be 14. I also know that this is the same angle, so you could really use either side, it doesn't matter. Okay, so I'm looking for some relationship between my opposite and my adjacent. So if I look at my trusty SOHCAHTOA, I know that opposite and adjacent fall under TOA. So I'm going to use tangent of f to be 16 over 14. So that means that f is going to be inverse tangent of 16 over 14. Okay. And if I plug that in my calculator, I will get 48.8 degrees. Okay, for your homework, what I would like you to do is take a look at example 9 and not have a worksheet for this, so just example 9, example 10, see if you can solve for our missing values. Say in example 9, I'm solving for the Greek letter theta, which usually represents an angle. Okay, and then for example 10, I'm solving for the Greek letter beta. Okay, so go ahead and give those a shot, and I will also upload a video afterwards explaining how to do these problems, but just for homework, try example 9 and example 10. Alright, that's it for this. If you have any questions over these notes, let me know. Otherwise, have a fantastic rest of your day.